Hey guys, hello again. Welcome to this week's discussion on naive Bayes. So this week is really the first week that we've talked about machine learning. So there's a couple of topics that are kind of important to talk about. So let's just start by talking about what machine learning is. So in machine learning, your goal is to classify samples and give each sample some label, right? So kind of in the canonical example, we're talking about spam and ham for email. So you're going to get an email, and your goal is going to be to classify that email as either spam or ham. Okay. Now, when we're doing machine learning, we'll usually be given some set of data, and we need to split this data up into three different types in order to create our model. So the first set of data is what we're going to call training data. And this is data that's going to be used to train our model. So this data is going to be used to estimate the parameters of the model. When we talk about naive Bayes later, this training data is going to be used to estimate our probability tables. We'll have a set of validation data. This validation data is going to be used to kind of tune the hyperparameters of our model. That can sound a little bit vague right now, but you can think of these hyperparameters as like features in your naive Bayes. So maybe you can use a wide scope of features, but probably you don't want to. Probably you only want to use features that kind of make sense for your model, right? Because you're going to train the model on the training set, and then you're going to test the validation set, and if it performs poorly on the validation set, then you can go back and train your model with a different set of features. Right. The final set of data is going to be the test set. This is how we're actually going to score the model that we've trained. So this test set is going to be kind of in practice like live data that you get going into your model. So if we're talking about spam again for some website, maybe Gmail, your test set is just going to be kind of live data that you get. Okay. So you train the model on the training set, you tune the features with the validation set, and then your test set is going to be what you really care about in practice. Alright, so that's very simply what kind of any machine learning problem is going to try to tackle. Now, before we get into talking about exactly how our naive Bayes model is going to work, we have to kind of learn how we're going to use our training data to train our naive Bayes, how we're going to find the probability tables for our naive Bayes, right? And to do that, we're going to use this thing that's called maximum likelihood estimation. So what does maximum likelihood estimation do? Well, say you're given a set of data for your training data, and this data comes from some probability distribution that has a parameter p. Your goal is going to be to find the p that best explains the data that you got, right? So what value of p would make it most likely for you to see this data, okay? So let's go through a quick example here. Here I have an example where you flip a coin 10 times, and your results are going to be 6 heads and 4 tails. The coin has a probability p of rolling heads and a probability 1 minus p of rolling tails. So with maximum likelihood estimation, we want to find the p that makes it most likely that we get this set of samples, right? So the p that makes it most likely that we find 6 heads and 4 tails. Okay, so how do we do that? Well, the first step is going to be to find what the likelihood of seeing these sample points are, right? So what's the likelihood of seeing 6 heads and 4 tails in terms of p? Well, these are all independent coin flips, so it's just going to be p to the 6th times 1 minus p to the 4th, right? So the probability of rolling heads to the 6th power because we rolled 6 heads, and the probability of rolling tails to the 4th power because we rolled 4 tails. So this is the likelihood in terms of p of seeing the data overall. So we want to maximize what this value is. So we want to find the p that's going to maximize this term, p to the 6th, 1 minus p to the 4th. And to do that, we're going to have to take the derivative of this and set it to 0. Now, usually, instead of taking the derivative of the likelihood term, we're going to work with log likelihoods because it's going to be easier to take the derivative, and the math just works out easier. So let's compute the log likelihood of this expression. It's just going to be 6 log of p plus 4 log of 1 minus p. And then from there, we can now take the derivative of this log expression to get something that looks like this. So the derivative of the first term, 6 over p, and the derivative of the second term, negative 4 over 1 minus p. We're going to set this derivative equal to 0 because, again, we're maximizing. So we want to set the derivative equal to 0. And then when we solve, we get out that p is equal to 6 over 10. right? So this is going to be our maximum likelihood estimation. All right, so it's pretty straightforward. But again, these are the steps for you. So step 1, find the total likelihood of the sample. Step 2, take the log likelihood. Step 3, take the derivative and set it equal to 0 because we're maximizing. And then step 4 is going to be to solve. Right? So these general steps are going to work for kind of any maximum likelihood problem that we see, not just one that looks like this. Okay, so this is how we're going to estimate the probabilities for our naive Bayes model with these maximum likelihood estimations. All right, so moving on, let's talk about Laplace smoothing. So again, we have some set of training data, but say that our training data isn't very diverse. Say that we only have 4 points for our training data, and what we see is 4 heads and 0 tails, so we never saw any tail flips. Well, what would we estimate the probability of this to be based on maximum likelihood? Basically, we would just estimate that the probability of heads is 1 and the probability of tails is 0. So why is this a problem? Well, in practice, the probability of any event is never going to be 0, right? And having a probability of 0 is really going to skew our distribution. And as we'll see for our naive Bayes model, if we have any feature with a probability equal to 0, that's going to basically make all the other features irrelevant, right? Because we'll have a weight of 0, and at that point, once we have a weight of 0, the total probability is going to be 0, and then it kind of ruins our model, right? So we never want to have a probability of 0 anywhere in the model. So that's why we're going to use Laplace smoothing to kind of try to smooth this data out. So here in our example, we'll use Laplace smoothing with a strength of 1. So what does this say? Laplace smoothing basically says that instead of saying that we have 4 heads and 0 tails, we're going to say we've seen one more sample in each category, right? So we're injecting these false counts into our sample data. Now, if we pretended that we saw one more in each category, then instead of having 4 and 0, we have 5 and 1. And now our estimation looks more smooth, right? So now our estimation for heads is going to be 5/6 instead of 1, right? So now we've eliminated the zeros from our probability model, and that's a good thing. And then going off of this, if we had Laplace smoothing with a strength of 2, that would just mean that we saw 2 more in each category, so these numbers would be 6 and 2, and then so on. So what does Laplace smoothing really do mathematically? Basically, it makes the distribution closer to uniform, right? So imagine if we had Laplace smoothing of 100, well, the probability of heads would be very close to 1/2 then, right? And if we had Laplace smoothing with infinite strength, then the probability of heads would be exactly 1/2. So what Laplace smoothing is really doing is it's making our distribution look more uniform. Moving on to our final topic of naive Bayes. So naive Bayes is just going to be one of the machine learning models, and basically the way the model works is we assume a BayesNet structure that looks like this. So Y is your label, Y is what you're trying to estimate. So if we were doing spam or ham, Y would be whether an email is spam or ham. And then all these things that Y points to are going to be features, right? So you'll have n features, and we'll assume a BayesNet that looks like this. All right, so what's special about the structure of this BayesNet? Well, first of all, in this BayesNet, each feature is independent of all the other features given the label, right? So F1, Y, F2, this is going to be a common cause, and a common cause when the middle one is observed is independent, right? So F1 independent of F2 given Y, and that's going to be true of all pairs of features. This is useful because it allows us to write the full joint probability as follows. Probability of Y and F1 and F2 all the way to Fn. It's going to be the probability of Y times the probability of F1 given Y, and so on and so forth. And this can just be read off from the structure of the BayesNet, right? So having tables that look like this is an assumption that just simplifies the math and the size of the tables, right? So it makes it easier to compute what our values are. And then basically when we get some test data sample, we're going to compute all the features for that sample. We're going to calculate the joint, the probability that Y is spam given all the features, and then the probability that Y is ham given all the features. And then we're just going to take the label with the highest probability, and that's going to be our label. Alright, yeah, so that's pretty straightforward. If you want to see an example of this, there is one in lecture that Professor Abeel went over. which uses the spam ham example. So I encourage you guys to check that one out. Alright, so this week was pretty short, but that's basically all I have to cover. So good luck on your homeworks, and see you guys next week.